So hi, my name is Santi. I'm here to talk about the paper that I have so far with my supervisor, Nico Payer, and his collaborators, Manhei Gordon Lee and Scott Melville. And I'm a cosmologist, so normally what we do is that we study the universe at its largest scales, and in particular we focus, myself, on the CMB anisotropies, so the temperature is not exactly the same in every direction, and the large-scale structure with roughly means why our galaxy is located at that point in the sky. We know we can measure this very well with satellites like Planck, and we know the thermal history of the universe very well. We knew when matter was important, when dark energy kicked in, when radiation was important, so we can turn back in time and take these correlators and study some initial form of those that we're going to call curvature perturbations that are seated at the end of inflation. Inflation is just an epoch of accelerated expansion that has another property besides creating these things, and is lowering the energy scale from some high energy regime that we call the UV, the ultraviolet, to some low energy regime that we call the infrared or the IR. Now the IR can also be described with something called effective field theories, the EFTs. And there are people that know a lot about the EFTs. That is not my case, or in general any cosmologist case. That is people from amplitudes, people that work with particle physics, or people from condensed matter physics. But this talk was tailored to particle people, so that's why I give them credit. So the question that we answered is, can we use amplitudes technology to study cosmological correlators? And the fact that I have this on a paper is yes. So we're going to divide the talk into 3 parts. I'm going to first talk about the theoretical framework for cosmology. Then I'm going to go back 60 years in time to discuss how people did this in the 60s. And then I'm going to try to marry both concepts in something called off-cell wave function coefficients. So first of all, I try to explain how to compute this thing. And normally we use this equation. That is called the in formalism. This is terrible. It's very difficult to compute. It has multiple integrals, and in general, it's very convoluted. So what people did was going back to quantum mechanics, and I definitely have something like a wave function that I can integrate over and get the expectation value of the thing that I'm measuring. In cosmology, it's a bit more complicated than just taking the position of a particle, because you have to take the value of the field at the end of inflation, this small phi here. So rather than having to do this integral, you are reduced to compute this thing. The question is, how do we compute it? Well, we use something called a path integral. So we just try to sum over all possible field configurations throughout inflation that start in a theory that we really understand very well, that is a free theory, it's the Van-Stevis vacuum, and that end at some particular value of the field, small phi. This is slightly different from what people use in amplitudes, where they just take particles that start free and end free and just interact in some middle point. And this condition is basically called the Van-Stevis vacuum. And it's the main difference between this path integral and this path integral. We normally can expand this thing because it's just a functional and a variable, so we can expand it, and rather than having just products, we have integrals, but that's that. And these things are called wave function coefficients that can be computed in perturbation theory, which is very familiar to anybody that has done particle physics or has done condensed matter physics. And the analytic structure of these objects is really related to what we see in the sky, these 2-point functions that I mentioned at the very beginning. The Feynman diagrams are slightly different from the thing that you would see in pop science, because we have this line here that is just the end of inflation, and that's why we have 2 different kinds of lines. We have external lines that go from the boundary to the bulk, and that's why we call them bulk-to-boundary propagators. And we have internal lines, like this one or these 2, that just go from a point in the bulk to a point in the bulk. We are super original naming things, as you can see. And now we're going to the past. We're going to talk about amplitudes. In the 1960s, people didn't have access to super good particle accelerators, so it was very difficult to guess what was the actual theory, for example, for the mass of particles, or the actual theory for hadrons. So they choose another path. Rather than doing very fundamental things, we're just going to use symmetries and fundamental principles to constrain everything so much that there was only one answer. So normally what people do is summing all these things and then doing this integral, and then you have an observable. Let's not do that. Let's just use principles and symmetries to fix these things univocally. This was not successful because it's way too ambitious, but it was really successful in studying a particular case. That is, at really low energies, studying the scattering of very little massive particles. For example, pions in QCD, which is one of the things that was quite trendy when this was developing. The thing is that as it's done for really low energies, one can also use effective field theories. A very toy model for this is a light field phi, a heavy scalar x, and if we're only looking at the scalar of phi, we can use these interactions rather than these ones. And the coefficients that appear here are called Wilson coefficients, and they're going to be fixed by some UV physics. And the kind of interaction that we can have, phi to the fourth, phi squared, dimension squared, phi squared, are going to be fixed by some IR symmetries and some boundary conditions, as the ones that I discussed before. This is a bit more technical part, but basically the idea is that this number here, AS of t, is going to tell you how the scattering of two particles works. It's going to depend on the center of mass energy, S, and the momentum transfer t. And the drawing is going to be this one. The point is that these x's here are related with internal lines that have a particular mass, and this x here, followed by a red line, is related to a loop diagram. The most important point is that this extension to the complex plane allows you to build this object that is called a dispersion relation, that is satisfied by any complex function. Basically, I can fix its value, knowing the value of the function at some points, and this integral, that is the discontinuity along the branch cut. So we can build some rules. That is exactly the way that you fix these Wilson coefficients in terms of the UV physics. How do we do it? We know the right-hand side. That we're never going to know, because it's this horrible thing that depends on really high energies that you are never going to measure. Ideally or practically, you're never going to be able to access this. But we can do a Taylor expansion of this thing here. We know that it's going to have a value when S and T are equal to 0. It's going to have a second derivative, a third derivative, so on and so forth. So if you equate equation 11 and equation 12 when S, T, and U are really small, you can fix these coefficients in terms of integrals of this form. And this is what is called a sum rule, because it's literally summing thing to fixing this. That's it. That's what a sum rule is. A coefficient from low energies fixed in terms of integrals at high energies. So how do we do this in cosmology? Well, first of all, we need to build an analogous to this scattering amplitude, and the way that we do it is extending the wave function coefficients. Rather than analytically continuing the momenta, that is the thing that people did in the 1960s, we first add a new set of variables that you can think of as the energy of the external lines. But we do not analytically extend the internal lines. And it has an interpretation in terms of something called time order in-out correlation functions, but it's really some mathematical mambo-jumbo that I use to convince people that this is important when I talk to this about mathematicians. So what is the kinetic structure of this new object? Well, we're only going to look at one of the energies, this omega-1, and we're going to promote it to a complex number. And the thing that we found, which was very curious, is that the location of the singularities is going to be given by conservation of energy, which is something super naive, but is incredibly present. So this is the energy of the external lines, this is the energy of the internal lines, and whenever this is equal to 0, we have a singularity. For example, for contact diagrams, all the lines land in the same vertex, so there is a singularity when omega-1 is equal to minus the sum of the other energies. Or in an exchange diagram, as I have this internal line, there's going to be a singularity when omega-1 is equal to minus omega-2 minus capital omega. The punchline is that all the singularities are always located in the real axis. And with any chance, they start at a particular negative number, not at 0. So the drawing is much simpler than the other one. They just take this form. They just take this shape. And because this is a complex function, it also obeys this dispersion relation of fixing things in terms of the value at some points and the integral along the branch cut. Now, there is a small couple of caveats compared to amplitudes when we talk about cosmology. As I discussed before, their interactions are constrained by two things: the symmetries and the boundary conditions. In amplitudes in particular, you have Lorentz invariance, basically the speed of light constant and all the business associated with it. And then the LZ reduction formula, that is a fancy way to say that particles to the infinite past and to the infinite future behave nicely, they don't do weird things, and they are free, they have a mass, they have a momentum, that's it. This is not true in cosmology, not by a long shot. Because first of all, we have a boundary. So you're breaking Lorentz invariance. Lorentz invariance requires that you are able to go through any constant time slice, and that is not true in cosmology. And secondly, interactions do not turn off in the future. When the inflation ends, even though you're at really low energies, there are still interactions taking place. So you cannot drop some of the interactions just because reasons. Which means that you need to enlarge the list of interactions that you're going to allow. For example, this one does not appear in amplitudes, but you need it there. And these are the ones in the bulk. And then this monster is the thing that you need to add because you have a boundary. If you didn't have a boundary, you just need to add one more number. Now that you have a boundary, you have to add all these numbers. But we can still do the same thing. We can just look at the left-hand side from the low energy limit, just taking omega to 0, and at the right-hand side as something encoding the UV physics, this integral encoding the high energy physics. And if we evaluate these integrals, we're going to have some rules. The particular thing is that we recover the one from amplitudes, we check this, is the same value, and we get new values for these ones, which are the ones that we needed to account for the presence of the boundary. So overall, we are 60 years behind the people from amplitudes, but we are quite confident that there is an analogy between what people did in the 1960s and what we're doing today. In particular, we are trying to translate everything looking at scattering amplitudes and offset wave function coefficients. And we have been able to bridge the gap and knowing where to add new points and when to reduce them, and in particular, what kind of interactions we need to add to account for the same phenomena in amplitudes and in cosmology. But we want to do more things. There's, for example, the discussion of UV bulk unitarity. If time evolution is nice, probability is conserved, how is this reflected at low energies? Because it's not that trivial. We also want to build positivity bounds. It's a thing that was developed recently for amplitudes, that it has been really useful to study effective field theories, but we have not been able to do it quite properly for cosmology. And finally, that is the thing that I'm doing right now, is translating even more amplitudes technology into the study of theoretical cosmology. Thank you very much.